Our ignition control modules feature several innovations. The wire bonds in our modules are thicker than the original equipment part by design. If the system is under stress for any reason, these bonds have to carry a higher current than the OE design can handle. This additional stress is usually due to other components degrading over time, like ignition wires or spark plugs or coils. These wire bonds connect the transistors to the circuit board. Our modules also feature advanced ASIC chips. ASIC stands for Application-Specific Integrated Circuit. The ASIC is the black rectangular component, right here, resembling a centipede. It's the brain power of the module. Fast start circuitry. When you rotate the key in a vehicle equipped with our module, the first coil is fired within 1/3 of a crankshaft revolution. Without fast start circuitry, 2 complete revolutions are required to fire the coil. This is a critical advantage during inclement weather. We beat competitors to market with this innovation by many years. Transistors inside modules get very hot. Another feature of our modules is copper heat sinks. We ultrasonically weld copper platforms between transistors and backing plates to transfer this damaging heat away. You can see the copper platforms right here. We've been utilizing copper heat sinks and fast start circuitry since we began manufacturing modules over 30 years ago. This innovation demonstrates advanced manufacturing capabilities. Ever wonder how a manufacturer produces products consistently to the same output levels? If they're doing it right, they're using laser trimming technology like we have for more than 3 decades. Different circuit designs call for specific flow levels, which must be adjusted to very tight tolerances. We manage these flows through 2 applications of laser trimming technology. Here's how we do it. The first level is called passive laser trimming, and it is used during the manufacturing process of the circuit boards themselves. Resistance is measured in the circuit board connections, and where resistance needs to be adjusted, lasers are used to trim precise amounts of the conductive material away. The second level is called active laser trimming and is used on fully assembled modules to precisely set the complete unit's output. The resulting accuracy and consistency means improved performance and reliability. As you can see, there are many advantages to our modules: thicker wire bonds, ASIC chips, copper heat sinks, fast start circuitry, and laser trimming. Advantage: Wells.
Hey, welcome to another Wells Tech live training event, and we've got a cool one today. Excellent. We're going to be talking about comparative or relative compression testing.
Yeah,
Doesn't that sound like fun?
Yeah.
Yes, and it can tell you a lot of things once you understand what you're looking at. And it's a great diagnostic tool, and I am sure if you have a scope, you are going to be using it after this class. Okay, but before we get started, we first have to do the T-shirt contest. Yes.
Show them both sides.
Both
it's a really
sides,
nice T-shirt.
yes, on the back. Yes, with
You know,
the
only a
wings.
select few have this T-shirt.
That is correct. That is correct. You don't have one.
But I do.
You do?
And I wear it when I'm out in my yard working on my Austin Healey.
On your Austin Healey. Okay, what?
I do have one.
That's, for mechanics, that's like going to hell.
For engineers, it's like being in heaven.
I know. Nobody can figure it out. Okay, all right, here's the question. Earlier Chryslers had a special starter on them, and it had a special name for it. It would crank a little slower and draw a little less amperage. What was the name of that starter? First one to text it in or email it in will be sent a T-shirt like this of their size.
How good?
All right.
How good?
So there you go. There's your question. Okay. Relative compression. Relative compression. And
That's when you stick all the aunts and uncles in a phone booth.
That's right. Yeah. How many can you get into a phone booth at once? Into a Volkswagen. All right. What is relative compression?
Well, I mean, think about it for a second. We got a V8 engine sitting there in front of us. It's got 8 holes, 8 pistons.
Right.
Each one of those is going to have an individual different amount of compression based on the compression ratio of the distance of the piston moving up and down and barometric pressure. So if you take the barometric pressure, and you multiply it times the compression ratio, you get approximately the amount of mechanical pressure you'll produce in that engine, minus some losses for leakage and all, but you can come up with 120, 30 pounds of pressure in a cylinder just in the mechanics alone.
Right, and that's what we're going to be looking at. We're going to take our scope. We're going to show you how to do this right on a vehicle too. But we have our scope in front of us. We have our Virus right here, and we're looking at a pattern. I'm going to bring it up on the screen in a second so you can see the pattern that we're looking at. And as the starter turns, okay, first what we did is we amp clamped the battery feed to the starter, okay, and cranked the engine over. And as we crank the engine over, and as compression increases, our amperage should also increase, right?
Yep.
That's how an AC DC motor works, right?
Well, that's how a DC motor works.
DC motor, okay, all right. All right, so
Yeah.
let's go from there.
Well, you know, one of the fun things for me is people like Mark. I'm sitting there at my desk this morning, totally innocent of anything, and he walks up to with this waveform and says, "Mike, what do you think of that waveform?" Well, okay there, Chief, let's take a look at it and see what we can figure out about it. So here's the waveform here, okay? Now, the first thing you gotta do in a deal like this is draw yourself some extra lines on there so you know where you're at. This is a really important step,
Right.
because when I first saw this line, it's like, well, compared to what?
Yes.
You know?
What is
so
that?
We need to do that. So first of all, we're gonna put a y-axis on here, and then I'm gonna put an x-axis on here.
Okay.
The most important thing that this is telling you is, first of all, this is when the waveform started, when your scope triggered off and started recording the changes relative to time. And what it's telling you right off the bat is that all your changes are something that happened above the zero line.
Right.
This is a DC waveform. This is a varying waveform. And then you told me the other piece of key information. This is an amp clamp waveform.
Right.
Now what that means is we're not looking at the usual voltages here, which is what you normally get. We got an amp clamp clamped around that big heavy red cable, and it's telling us what the current pulses look like going through that wire.
Right.
Okay?
Exactly
now,
right.
That's pretty important, because now we know that this particular value here is 0 amps, and then this value here is somewhere around 200 amps. I don't remember exactly.
Right around that area.
In
right?
that general neighborhood. Well, just this little bit of orange that's on the drawing here adds a tremendous amount of information in terms of looking at this and trying to find out what we got.
Right.
Now, in order to interpret this waveform, we need to understand a little bit more and remember a little bit more of what those teachers taught us at tech school. They were great guys.
Yes,
and gals.
absolutely.
And you know, we all owe a debt to those people who took the time to really care and to teach us, because we all learned it. I surely did. Okay? I didn't know it all by myself. You know?
Right.
They
No,
didn't
no,
teach me this in engineering
Doesn't
school,
happen
right?
through osmosis. That's for
No,
sure.
it really doesn't. And I appreciate those people and all what they did for
I
me.
do too.
Okay? So now, let's look at this waveform a little bit more. And I want you to notice two things. One is we got a series of peaks here. Whoa, and look at this.
What happened to that peak?
That one didn't hardly draw anything in way of current.
Right.
Doesn't that stand out there like a big sentinel on the hill saying, "Hello, folks,
Gee,
look
there's
at me,
something
look at
different
me."
here.
Yeah, okay. So this, if you want to put a big word, is an anomaly. Something is
Yeah.
different in that spot, okay? Then, the other thing that we can notice about this is that these pulses here are all about the same amplitude, okay?
That is correct.
Now, that's a key piece of information. Now, what we ought to do is remember something from our instructors about how DC motors work.
Yes.
Okay? DC motors are voltage sensitive for speed. So if you take a starter motor, and who hasn't done this, It's off the car, it's laying on the ground. Well, is it a good starter motor or isn't
Or
it?
isn't it? Right.
So you step on the motor and you grab the booster cables and you jab it to it and it goes,
Right.
and it'll jump off the ground if you didn't have your foot holding on it.
Sure.
Well, there's value in that, and then there's a little bit of not value in that. The value in it is, you know, the motor rotates. You know that it'll run up to some open circuit speed, but what you don't know is the load capability.
Right.
You really think about it at the end of the day, what do we want the starter motor for? To crank the engine.
It's all about load.
It's all about load and it's all about torque. And
Right.
it turns out that in DC motors, they are voltage sensitive for speed and they are current dependent for torque. So now let's go back and look at our
Very,
waveform.
very good point.
Yeah, so here we go. We started off, and maybe this really should have been closer to 0. I should have put the orange line under there a little higher. But the idea being is we started at some point and we hit a peak and then we came back down.
Right.
That peak represents the maximum load of the engine on the starter related to hitting its peak mechanical compression.
You know, and that's a good point. And if you look at the scope pattern, an entire scope pattern of the cranking event, what you'll see is it'll be way up here, drop down, and then do that.
Yeah, you get that initial thing, it's called a locked rotor current impulse.
Okay.
Yeah, well,
Maybe that should have been the
grab
question.
that one out of thin air, right? Yeah, so when you want to test a motor for its torque delivery capability and basically to make sure that the motor is healthy, one of the things you do is a locked rotor test. You just simply lock the rotor, throw the current to it, and see how much you get. You don't want to do that for very long.
No, that sounds kind of, they're pretty
But a
strong.
locked rotor test is a standard electrical test they do for electrical motors.
Okay.
Okay? So when it's under locked rotor conditions, it draws the maximum current, but this isn't locked rotor.
Right,
This
no.
This is 130 or 40 pounds, depends on the engine, of course,
Yeah.
and the compression ratio. That's opposition to the rotation of that starter.
Right.
And as it opposes the rotation, the current pulse into the starter will increase to provide the torque to overcome that.
Right.
Okay? So now we know that each one of those is a compression piece of the puzzle.
Right.
All right? Now, what's this little green thing doing in there?
What is that little green thing?
Well, it isn't a monster or alien or something from a different planet. What it is, it's our ignition pulse.
Okay.
Okay? So now think about it. We know that we want to advance the timing to start the ignition event at some point before top dead center.
Right.
It could be a nominal 10 degrees, it could be 25 degrees, it could be
Very
whatever
much
the
so,
computer wants it to be. So now, one of the other things we can learn from this waveform is by looking at the ignition pulse and looking at where it occurs just before the peak pressure pulse, we can know that our timing is right.
Right.
Think of the Cadillac 3.6 liter engine.
Okay.
And this is really true with anything that has variable valve timing. Okay. In the Cadillac, they have a little trouble with oil pressure sometimes because of lack of enough oil in the crankcase.
Right.
Okay. So think about what that variable valve timing is supposed to do. It's supposed to give you an active cam to give you peak power output.
Right.
So you can look at this pulse and look how it moves up and down the leading edge of that peak waveform, and you can watch your variable valve timing working.
You should be able to. I'm not sure if that works during cranking or not.
Well,
If it would really change that.
it might not, okay? But the point of it being is that the relationship of this relative to here for sure tells you something about the mechanical timing
does.
Of the engine.
Yeah, and I love that. You know, the thing is, if a vehicle comes in and it's running crappy, okay,
Yep.
and you suspect that maybe there's something going on with that timing chain. The first test you should do is that relative compression test. I would think it's so easy to do. And if you see this green line over here instead of at the pinnacle or the peak point or near that peak point,
You know, something's not right.
something's not right.
Yep.
Something's not right with that valve timing.
But think about our 3.6 liter. It's a sidewinder, it's east-west of the engine compartment.
Yep.
It comes in inevitably just plan on it. This is going to happen to that cylinder that's way back down in there somewhere where you can't get to it. Okay? So now think about the amount of effort involved here in doing a compression test.
Absolutely.
You got a dead hole. The OBD2 is telling you something is wrong with that particular cylinder back there. You can walk up to this engine, put your current clamp on it, run yourself a pattern, and you know that something is radically not right in this particular cylinder.
Right.
Compare that to the idea of, oh, something might not be right here according to OBD2. Let's go back in there and pull that plug, wire in or screw in our compression tester, and now we run a compression test on it.
And it took you 3 hours to get there.
You got my point.
Right.
Exactly.
Exactly.
So this is a wonderful test in terms of allowing you to walk it up, slap something on that battery cable, look at it on your snap-on or whatever else you got that works as an oscilloscope for you, and you can find this bad boy, and already you've got a lot of information.
In a hurry. And you know, the more I play around with this test, the more I use it.
Yeah.
And because the more I'm understanding it and what I'm seeing and different examples of it, it's become a regular test that we use.
Yeah, you don't want to have to be chasing in the back of that engine trying to find that cylinder hole.
No.
So really what you have here is that when it hit this particular spot, what was going on there is it didn't have any pressure, mechanical pressure in that hole.
Right.
And so when the starter came to that point, it didn't need any current really to push that piston up against that mechanical pressure.
It was just kind of free spinning at that point, wasn't it?
Yeah. So now you look at this thing, and one of the other things that we talked a little bit about this morning is look at these jaggedy lines in here.
Yep.
You ever heard of a commutator? We've
yes.
got that in our DC starter motor. And every time it switches, it's trying to make itself go around in circles.
Okay.
Every time it switches, it leaves you a little impulse there.
As it goes to the next brush.
Yeah.
Yeah.
You know,
very cool.
when I talk to mechanics, and I have one who's a wonderful friend of mine by the name of Tom, and he sees stuff like this, and he says, well, gee, it looks like a bunch of gobbledygook. You know, he really is puzzled by it. And I thought, well, you know, Tom, it's not that bad. Put yourself some orange lines in there. Figure out where you are. Realize that you're measuring current. Realize that each one of these pulses represents a peak current draw by the starter motor.
Right.
Okay? You get the peak current draw at the maximum mechanical pressure in the cylinder.
Yep. That's exactly right.
And
that's how you have to envision that in your head.
Yeah.
Is that's the peak of the compression.
So I showed this to him, and I said, well, how do you know that I'm looking at a V8 engine here?
Yes.
And the answer is, well, 1, 2, 3, 4, count the missing one, 5, 6, 7, 8. How easy is that?
Yep, that's right. And if there's one missing, if you got an 8-cylinder engine and you only see 7, or if you got an 8-cylinder engine and you only see 4, one cam's not working.
Yeah.
Right, exactly.
So the idea about waveforms like this is they have a ton of information.
Yep,
okay?
they do.
And you just have to sit down and figure out what it is that you're looking at.
How does it relate to the mechanical?
Yeah.
You know, and that's what you have to do.
And how much easier is it to go looking for something here than it is to dig down through that engine?
Absolutely. You know, before we go test on the car, there's one other thing I want to bring in here, and it's my old nemesis. By the way, when we're testing on the car, our last lesson, which was on Ohm's law, we were testing an injector. And what we did was we used Ohm's law, we measured the voltage going in, we measured the resistance, and of course, if you take the resistance by Ohm's law and divide it into the voltage, you should have the amperage. And the amperage by mathematics should have been right around 1.1 amp, and we were about 0.9. Now, is that close enough to fix a car? Heck yeah, it is. You know, you're never going to get to an exact measurement when you're doing that type of thing. So how can we relate Ohm's law to this?
Well, you really can.
Okay.
So now let's think about it. How much current would a motor draw? Okay, it depends on the load that's on it, and it depends on the effective resistance of the motor, including some time delay things related to the inductance of the motor. So you could take this pulse here, approximately 200 amps, and you could calculate, using Ohm's law, the effective impedance for current flowing into that motor.
Into that starter motor. So what we're looking at on each one of these peaks is highest resistance point, right?
Highest resistance to the mechanical rotation of the engine.
Yes.
Yeah.
Right. So that you think of that as a high resistance point.
You know, it's a funny thing when you really get into physics and engineering and stuff like that. You find that systems are related. You got mechanical things we deal with all day long. We know if we push this hard on this particular point, we'll get that much movement or whatever's involved. You can calculate all that. About the same thing with electricity.
It's the same
about
thing.
the same thing with magnetism.
Yep.
There's rules of the road that show you about what the number is supposed to be
Right.
like. One of my pet peeves is when the guy comes back from the engineering lab and he'll tell me that, well, we tested the coil for you, Mr. Dale, and the answer is that it produces 11,291.06357891 volts. Okay?
Wow.
They bring me numbers like that all the time, and it's like, peace, brother. It's 11,000 volts. Your system of measurement isn't capable to give me a number like that.
Right.
And even if I had a number like that, what would I do with it?
It wouldn't matter.
What I want to know is about where we are.
Right.
And this is really a great impact statement for students in the world of mechanics.
Yep,
They
it
bring you
is.
the voltmeter and say, well, now, Mr. Dale, it reads 11.39715 volts. Is the alternator charging or not?
Yes.
And the answer is no, that alternator is not charging. It's below 14.2 volts. It doesn't matter if it's such a long number as all of that.
Right.
The answer is it's not at the voltage regulator setting. You got a trouble there.
Yep.
Okay.
So the point is, don't
Obsess over a million.
Right, don't obsess over it.
That's the biggest downfall
Right.
of digital outputs.
Just like this. Okay, if we do a relative compression test like this on a vehicle, and we see this green line, which is our trigger point for the spark on one of the cylinders, it doesn't have to be number one, right? And we see it over here. Is that telling us that that timing chain is bad? Not necessarily.
But I'm telling you, it's way different than what you expected.
Right, it's different than what we expected. The next step then I would take is to look at crank and cam sensor together with a known good pattern to see whether or not that timing chain is actually lined up. But what this will do is lead us there to do that test.
You ever watch those cowboy shows on Sunday afternoon when you were a kid on the television?
I still do.
Yeah, well, good. And what you learn from all of that is there's no silver bullet.
That's right.
Okay? You have to take individual pieces of data, fit it into the overall puzzle. This is what a tech does for a living.
That's right.
It's also
That's
what
exactly
an engineer
what we
does
do.
for a living.
Yep.
Is you take all the available information, you put it together in your head and say, you know, I don't care if it's 195 or it's 200 amps.
Right.
What I really wanted to know is that they're all about the same, except for when they're not the same.
Right.
That's what you need to learn
And that's how
from
they
that.
tell you to do a compression test with a
Yeah.
gauge today. Make sure they're relatively the same.
Yeah. So there's just wonderful information in this higgly-piggly drawing that you came
Yep.
and put on my desk this morning. And really, thanks for bringing it. You know, I look at this and I think about it a little while and I learn from it, and then I put a few little things together, like DC motors are voltage variable, but they're torque dependent on current.
Right.
And then, oh, gee, doesn't it all make sense?
It makes sense now.
Yeah.
Okay. Well, that's excellent, Mike. Thank
Well,
you so
yeah,
much.
You're more than welcome.
All right, I'm gonna
Very
grab the meter here.
Okay.
And I'm gonna go over to Dave, and we're gonna go do this on the car.
Oh, well, have fun.
All right, thanks again, Mike.
See ya. Take care.
You too. Hey, Dave.
Hey, Mark.
What you got going on here today?
An interesting Ford.
Okay, let's hear about it.
No check engine light. Missing really bad. The way I can tell it's missing, the engine's shaking, and you can go on the tailpipe, feel the pulses.
Okay.
The customer's complaining, oh, it's not running good. So we got to do a relative compression test here, and
Can you
See
hear
what
it
we
when
got.
you crank it over that it's low on compression?
somewhat, yeah.
Okay.
And you get kind of tuned to that.
So that's
by-
kind of leading you to
Right.
check a compression. Plus, it's unusual not to have any check engine light at all. If you have that, if you have really low compression, you would think you would have.
You would think it would pick it up, but
Right.
I don't know if that's somehow on these Fords they just have issues with their misfire counters sometimes. Because even the Mode 6,
Yeah.
completely good on all the
Oh, is
cylinders.
that right?
So it's but I've
Okay,
ran into that
so we're
before.
going to do a relative compression test, and we're going to see what it looks like. All right, cool. All right, let's do it. what we're going to do is we have an OTC amp clamp, 60 amp clamp. I'm going to put this on, and we're going to have it on 1 millivolt, 100 milliamps. You can use 100 amp, 200 amp clamp if you have it. That would work just fine, but these will work just fine too. It's going to be powered on and ready to go. And then we have our ground here, and we also have our trigger point is on the number 1 coil right here. And that's the trigger for the coil that turns the coil on and off. So when we see this fire, we know, or when we see this go off, we know number 1 cylinder just fired. Okay, and that's going to be our synchronization. Are we ready?
We're ready.
Okay, let's give it a try. Hold on here a second. Let me hit the record button. All right, Dave, anytime you're ready. That's good. Okay, we got a real nice pattern here.
Good.
All right. Now, if we take a look at this pattern, remember, trace number 2 is our trigger. So every time the trigger goes off, that means number 1 cylinder just fired. So we have 1, 2, 3, 4, 5, 6, 7 current draws.
Yep.
Okay, and this is an 8-cylinder engine, is it not, David?
Correct, 4.6.
Okay. All right, it is an 8-cylinder engine, and as you can see, we lost the second one in the firing order, right here. It dropped way off, came way down. I bet you if you would have stopped cranking right there, it would have just, dropped right down to nothing. But then it picked back up again when the resistance from the 3rd cylinder came up. So now, to know which cylinder this is, what we need to do is take the firing order, which is right here. And by the way, these are available on our website. It shows you where the cylinders are located, where your coil and plug is on this, that type of thing. And then the firing order, it's 137-26548. So cylinder number 3 right here is the one that's missing. So you did do a regular compression test, a pressure test on it, right?
Yeah.
And it was 0.
0.
Okay, so that more or less tells us pretty certainly we have a valve problem of some sort. Either a valve spring broke or a valve is burnt or something, right?
Correct.
Usually when you get 0, that's what it is.
Especially when.
Okay. Now, the other thing to look at here, which is very interesting, is can we use this for anything else other than to look at compression?
Really a good point. You're going to be able to tell how the timing is.
Yeah.
Because the way the spark is hitting towards the top of compression.
Very much so. And you can see that these trigger points right here are right near the top amperage draw of that cylinder. It's right near it. And that's telling me, you can see it over here too, that's telling me that that timing is right. It's pretty darn close. It's not alerting anything where I have to go and look at the cam and crank sensor and sync or anything like that. Now, if this was over to the side a little bit more, over here or over in here, yeah, I would definitely then look at the cam and crank sensor, compare them together, look at a known good value, make sure that it does line up properly, right?
Right.
Okay, so now the other part that everyone needs to know on this is, like, let's say you got a vehicle with 4 camshafts, so you got 2 on each bank. And if that is the case, what you need to do is to have a trigger point on the other bank also, just to make sure that all those cams are working properly.
Right.
Okay? Because otherwise you could have a chain loose on one side, not on the other, and it wouldn't pick it up. Now, if you had low compression on the other bank, you would see this one low, every other one you'd see real low, as far as the amperage goes.
Right.
Okay, play around with this. There's a lot of value in this scope pattern. By the way, our scope is set at 2 volts per division and also 2 milliseconds per division. Okay, so there you go. That's how you set up your scope. That's how you do this. Great test. Anything else you want to add?
Yeah, well, just to reiterate, it's
Sure.
just such a fast way of doing something that could take you half a day.
Oh.
Most of the cars now, you got to pull the intake to get at a cylinder.
Right.
This way you put it on here, you can tell right away if you got to go towards a compression problem or a spark problem. Plus, you can also get your ideas, we're saying, you know, about your timing.
Right.
So you can learn so much in just this little bit.
All
All
in
you
one
gotta
little
do is-
package right there. And how long did it take us to set it up?
And even the first time when I first
That's-
did this, 5 minutes.
Yeah.
At that.
Yep. Just remember 2 and 2,
Yeah. Yeah,
2
that's
volts
real
and
important.
2 milliseconds, and you'll be all set to go.
And
So-
you can go on any coil.
Right.
You know, as long as you got your.
And that's a good point too. You don't have to be on number 1. Let's say we were on coil number 6. Well, then the next one would be cylinder number 5, and you'd count it off that way.
From there.
Yep.
It's,
So it
it's a
doesn't
slick
matter.
test.
Go to the easiest one, right? And back probe there. But going to a coil is much better than an injector. Now, if you go to an injector and you back probe that and use that as your synchronization, you're going to be off because your injector is going to fire much sooner than the spark.
Way sooner.
Right.
A couple cylinders probably
So
almost.
you got to make sure that you do that off of a coil. Okay, Brian just handed me the results, and Roy gets it again. Roy, send me your mailing address. My secretary's probably got that already, but send it to me again, and this time, and your T-shirt size. And geez, you're going to have enough for the whole family here soon. We do appreciate you watching, though, Roy. All right, that's it. Okay, a gear reduction starter was the correct answer, by the way. Gear reduction starter. Chrysler started with those back in
way back.
long before my time. Okay, that's it. Anything else you want to add?
That should be good. Just
Okay.
Great test.
Yep, great test. Play with it, get familiar with it, and I guarantee you're going to be using it all the time. All right. We appreciate you being there. Without you being there, we would not be here. And we'll see you again next time in the Wells Tech Garage.